Hi, I am Aaron Goldfield, and I worked with my mentor, Tony Alcocer, to try to characterize rocket motor performance. Please note that descriptions have been simplified to comply with time limits. We did this because getting to high altitudes or to space can be difficult, but in situ testing can be a valuable way to gather data. We wanted to create a vehicle that could allow paths to be tested easily. We used the electronics and softwares listed to gather data on engine thrust, altitude, and other flight characteristics. We also wanted the project to be educational, providing insight into rocket design and construction, from fiberglass to propellant mixing. We knew that the vehicle had to be easy to build and affordable so that it could be widely accessible. It was also vital that the vehicle should be flexible, durable, and reusable so that it could be used repeatedly to test different things. It is important to note that our 51-inch tall rocket is in the middle of the rocketry range, in the sense that model and high-powered rockets can be under a foot tall or more than 7 feet tall. When constructing the body of our rocket, we chose to use a mandrel and 7 layers of fiberglass with epoxy, as determined with test pieces we made earlier. To prevent the epoxy-infused fiberglass from sticking to the mandrel, we first wrapped the tube in 2 layers of mylar. We also used peel ply to ensure that the outside was smooth. The nose cone required us to use a mold and strips of fiberglass, but otherwise we used a similar process. The motor mount, which also holds the fins, was made of simple materials: cardboard, wood, and styrofoam. A hose saw was used to ensure circularity of each of the pieces. Most rockets that are passively controlled use fins like these to maintain stability. For ours, we used old plastic laminate material that was similar to our fiberglass epoxy mixture. As per the label, this material was originally intended to be used by Lockheed in the 1980s, but it never was. In any case, we first decided on a shape in line with what was known to work well, since we were not trying to do anything experimental with the fins. After this, we laid down tape that allowed us to mark the exact shape and then used a jigsaw to cut out pieces. Finally, the intersection that was to be placed in the slot in the rocket body was roughened so that the epoxy would hold onto the fin with increased strength. To provide a place to insert the fins, we cut a slot into the fiberglass and motor mount that was aligned with the rest of the rocket body. In the images, you can see how one of the buttons that interacts with the launch rail is attached as well. Actually mounting the fins might have been one of the most difficult steps to perform as a beginner because it needs a lot of precision, and the tools and materials we used for it are a little bit less common. When we inserted a fin into a slot, we filled the slot with epoxy and used a special wood mount to ensure that the fin was straight in terms of coming out of the body. After the fins had been dried sufficiently, we mixed up more epoxy with cut up fiberglass, which increased its strength but made it thicker. In the image on the left, you can see how we used tape to ensure that the epoxy didn't end up in an unwanted place. After that, we cut our own parachute, allowing us to optimize shape and size. We chose a parachute with a 45-inch diameter and a hexagonal shape. The parachute was made of ripstop nylon, which is a strong, versatile material. Afterwards, the parachute is wrapped up and placed inside a fire-resistant Nomex bag to prevent damage during separation. This bag was simply a piece of fabric sewn together. We also made our own research motors using a modification of a common recipe. This recipe produces a very thick substance that is packed into special casting tubes and left to harden. While the electronic igniter serves as the starter, the reaction also needs fuel and oxidizer. The fuels are the HTPB, which is also used in the space shuttle, and atomized aluminum. The oxidizer is ammonium perchlorate at various mesh sizes. Traditionally, the recipe only uses AP200 and AP400, but we added AP90. These smaller, faster burning particles allow the aluminum fuel to burn more completely. Additionally, tepanol, which helps to hold the material together, was left out, since less than 81% of the propellant was solid. With a higher solid ratio, it would have been necessary, but leaving it out allows us to minimize gas production and therefore the creation of bubbles that could cause instability. Finally, the electronics. These were fairly standard. For the engine, the easy motor was connected and able to measure torque. A lithium battery powered a featherweight GPS module that connected to a ground station and one of our phones. The same battery powered the Altus Metrum Easy Mini flight computer. Connected to a 9-volt battery was the Stratologger flight computer. Having 2 of these computers provides redundancy, particularly since they control charges that are necessary for separation and parachute release. The charges are timed in relation to altitude and apogee. Our rocket used 2 types of charges, excluding the ground-controlled igniter in the engine. Firstly, small charges of black powder ranging from 1.75 to about 2.5 grams were used to separate the rocket. Afterwards, cable cutting charges cut zip ties to release the parachute from the Nomex bag. I have a quick video of one of our deployment tests now, when we were testing quantities of black powder as low as 1.25 grams. 2, 1, mark. And here is one of the charges that caused a zip tie. We had 2 of them for redundancy. We launched on July 12th from a flat near Stagecoach, Nevada, which was about 5 to 6 hours away. There, we attached the black powder charges and zip tie cutters and turned on the electronics. We placed our rocket on the launch rail and prepared to launch. Unfortunately, there was an anomaly. Here is a photo of the motor being pushed out of the rocket, which I'll get to later. Here is a video of that event.
3, 2, 1.
Here are photos of the electronics and failed motor following the first launch. Unfortunately, the first launch destroyed the thrust measuring electronics, preventing us from collecting the data necessary to characterize the difference between the 2 nozzles. We launched again as my mentor had an older motor that was still usable, but we could only collect standard data such as altitude and velocity. Unfortunately, slightly after apogee, the GPS module lost connection. Fortunately, we had other logging devices on the rocket, and it landed close to where we launched it from. Here is a video of that event.
Thrust on duty going in 3, 2, 1.
The following slides contain the launch data, but I won't spend long on them because there aren't an abundance of new conclusions to draw. After the launch, we inspected the motors to verify our theory regarding the cause of failure, which was that the excessive combustion in the motor caused an overpressure that quickly popped out the motor. Specifically, we had theorized that a common manufacturing defect in the cardboard casting tube had allowed a flame front to penetrate the windings of the tube, increasing surface area for burning. We were indeed correct, as we could see that the cardboard casing had been burned through, increasing reaction rates considerably. By cutting one of the grains open, we could also verify that there were no major bubbles in the grain, which could be another cause of failure. The few bubbles that there were very small. Despite the anomaly, we confirmed that it was possible to build a remarkably durable, reusable rocket with common materials and tools, and without using kit parts for any section of the body. Although we experienced an anomaly, we still learned a few things from the data. For one, the data shows how separation charges can affect altimeters and data logging. In all of our data across both launches, it can be observed that at the time the charges fire, the apogee has been more or less reached. In the case of both launches, a data point is recorded to have an altitude of as low as negative 5,000 feet or less. This is likely because the devices recording altitude, velocity, and acceleration depend on air pressure, which is increased temporarily when a separation charge fires. It also became evident that altimeters can disagree on altitude due to the usage of different methods or barometry. Altimeters relying on air pressure can't fully factor in differences in air conditions like pressure, temperature, or density. GPS-based devices must be programmed with awareness of the location of the surface, but still, GPS is more likely to be accurate than its alternatives. Finally, I would like to thank my mentor, Tony Alcocer, for his time and experience when helping to lead this project. I would also like to thank the Sonoma State University, NASA, and the N3 program for providing the funding and connections necessary to make this possible.